Okay, we're going to review Chapter 5 by looking at some old tests. And the most important thing to know in sections 1 through 3 over the approximation of definite integrals, i.e. quadrature, is this theorem here that says that basically polynomials are the guinea pigs that you try your quadrature rule out on, and it tells you how well it's going to do for general functions, namely if your method is degree of precision m, if it's exact for all polynomials degree m, i.e. exact for 1x, x squared up through x to the m, then the error in general for a general function, not a polynomial, is going to be, the global error is going to be proportional to h to the m plus 1. Global error means the after you've added up all the strips and compared it to the true interval from a to b, as opposed to the local error, which is just the error per strip. So if it's exact for degree of precision m, then it's order h to the m plus 1. Okay, on the first page of the first test, there's already a problem where that theorem is important. It says determine the weights A and the sample points R such that this is as high degree precision as possible and thus as high order as possible. So you just plug in f equal to 1, f equal to x and x squared, and try to make it go as far as you can. Choose A and R to make it go as far as you can. Now notice this is usually we have the integral from 0 to h because that's easier to convert to xi to xi plus h, but this is in terms of minus 1 to 1, but still exact is exact, so just plug in 1. Integral from minus 1 to 1 of 1 is 2, and f of anything is 1, so that's just a plus a, so we already get that 2a has to be equal to 2, so a has to be 1 just to get that far. And then you plug in x, integral from minus 1 to 1 of x, that's x squared, and upper and lower limit are the same, so you get 0. And f of x is x, so f of r minus r is minus r, f of r is r. Those add up to 0, so basically this is exact no matter what a and r are. So you keep going, x squared, integrate that from minus 1 to 1, it's 1/3 h cubed, x cubed, plug in the upper and lower limit, you get 2/3, and a times minus r. So f of x is x squared, f of minus r is minus r squared, f of r is r squared. And we already know that a is 1, so that's just 2r squared has to be 2/3. Therefore, r squared has to be 1/3, so r is the square root of 1/3. And basically, this is the Gauss 2-point formula here that we just derived. It's the best weights and sample points. For if you have only 2 points, it's the best weights and sample points, assuming we're integrating from minus 1 to 1. If you're integrating from 0 to h, you have to scale things appropriate. Now let's look at some of the true-false questions, the ones that are relevant to Chapter 5. Experimental order of convergence is order h cubed if a quadrature rule, approximating integrals, yields 0.0032 when h is 0.1 and this when h is 0.05. So h is cut by a factor of 2, the error goes down by a factor of 16, therefore it's fourth order, 2 to the fourth is 16, so it's not third order, it's fourth order. Round-off error is much more serious for derivative approximations than integral approximations. Yes, derivatives, you're subtracting two nearly equal things. Integrals, you're generally adding areas, so it's not near as serious. But derivative approximations, there's just no way around it. You're going to have round-off error problems. Just don't take h too small. Quadrature method is exact for all polynomials degree n. The global error is order h to the n for general smooth functions. False, it's h to the n plus 1. And almost every test has a problem like this where you need to know that theorem that we're just talking about. Sometimes I'll give you the coefficients and you just say how high degree precision it is. This, you're supposed to determine a and b, which make it as high degree precision as possible. This is a homework problem, by the way. So you just plug in f equal to 1, x squared, x cubed, and keep going until you determine what a and b have to be to get that far. And of course, it doesn't do any good to be exact for x cubed if it's not exact for x squared. So, okay, so you plug in 1, x squared, x cubed, calculate the actual integrals. F of x is 1, so that's AH times 1 plus BH times 1. You get, after dividing out the H, you get A plus B equals 1 and so forth. And already with, you really just need the first two formulas to determine what B and A have to be. These are the only values of B and A which will get you this far, but they actually get you even further because it asks, if it just asks what are the best choices of A and B, then we'd be done after this because there's only one choice of A and B that satisfy the two equations. But it asks what is the order, then you have to go and see, maybe you get lucky and it's exact for x squared also. You don't have any more control over what A and B are because they have to be these values to get exact for polynomials degree 1, but maybe you get lucky and it's exact for polynomials degree 2, and in fact you do get lucky, but you don't get too lucky, so it's exact for polynomials of degree 2, therefore error is order h cubed for general functions. Okay, one true-false question is interesting here. It says a quadrature method which is order h cubed will give a smaller error than an order h method for any h. No, that's not true. As h goes to 0, eventually the order h cubed method will be more accurate, but this method might have an error that's a million times h cubed and the other was just h, and for a while h is smaller than a million h cubed until h gets real small. So it's not true that the higher order method is better for any h, but it's better eventually as h goes to 0. Here's a section 5.4 problem, approximating derivatives. This time you're approximating a third derivative, and they give you the formula, so it's not undetermined coefficients, and you just have to expand u at t plus h. That you just need to memorize that formula. Then you replace h by 2h to get this one, replace h by 3h to get that, and take 1 times this minus 3 times that plus 3 times that minus that, add it all together, and you get u triple prime, which is what you're trying to approximate, plus this, so that must be the error in approximating u triple prime. Another section 5.4 problem, you're trying to approximate the second derivative, but notice that this is not symmetric. Normally approximate the second derivative u at x plus h minus 2u at x plus u at x minus h, but this is all moved over. It's evaluated to get 2h, h, and u, and if you expand those you find that the error is only order h because it's off-centered, whereas the other usual formula, the centered formula, is order h square. And here's another quadrature problem. The weights, the sample points for some reason are 0.5h and 0.8h, which is not a very good idea. Why would you choose sample points to be off-centered like that? But it's a test problem, so choose the, given that somebody's insisting that the sample points be 0.5 and 0.8h, what are the best weights? And it's just a question of plugging in 1x, x squared, and by the time you get the 1 and x, you got two equations for a and b, and a has to be 1 and b has to be 0. So it's basically the midpoint rule because that term disappears. And then since it asks, so it's not exact for x squared, therefore degree of precision is 1, therefore the global order is order h squared, 1 more than the degree of precision. Okay, well, I've skipped a number of problems. They're so similar. Again, find the weights given that the sample points are 0, 1/3, and 1h. What are the best weights? And you just plug in 1x, x squared, and solve system of 3 equations, 3 unknowns. But finally, let's look at a couple of problems here. It says a quadrature rule yields errors of 0.0064 when h is 0.01, and the 0.0002 when h is 0.0025. So h is cut by a factor of 4. The error goes down by a factor of 32. 32 is 4 to the 2.5, so it's 2.5 order. You could simply say that 0.0064 is m times h, this h to the alpha. This is equal to m times this h to the alpha, and divide the two equations to get rid of the m, solve for alpha, and you'll get 2.5. Second problem says, of all quadrature rules with n sample points per strip, the one with highest degree of precision is called what? Well, those are the Gaussian formulas. They're the ones with the, the Newton-Cotes formulas are the ones where you insist that the sample points be uniformly spaced, but that's not as good because the Gaussian formulas are the best because they choose the optimal sample points as well as weights.